Welcome to the pre-recording of lecture 35, which is the 18th session in the 8-week summer course. It is the first half of the beginning of week 7, so we are in the next to last week. Most of what we are covering in the remainder of this class is in some sense a reinforcement of principles introduced earlier. So we have introduced object-oriented programming. Object-oriented programming presents a model where objects and classes and hierarchies, relationships between the objects are important. So the title of this lecture is Class Hierarchies, and the goal is to present a geometric model of a parabola. So I will do this with a sequence of 6 classes. In the first part of this lecture, I will go through some slides to prepare the second part, where I will systematically run through each class. So we start with simple objects, points and lines. A parabola is defined geometrically as all points at the same distance from the focus, which is a point, and the directrix, which is a line. So by making gradually more and more abstractions of the geometric objects, we will arrive at a relatively simple, short definition of a class to visualize a parabola defined geometrically via a focus and a directrix. So that's the main point of this lecture. So let's start with points. And suppose we want to draw a point. So the class point, what that does is storing the coordinates of the point and the string representation. Now, if you want to draw a point, you have to decide on the color and the size of the point. A point actually is dimensionless. Normally, you couldn't actually see a point. So in some sense, drawing a point is a contradiction. A point is zero-dimensional. We can't observe this the same way we actually can't see one-dimensional objects, but we make them thick so they become two-dimensional. All right, so these considerations aside, we will have one widget throughout this lecture. So, and instead of having the GUI kind of determine the entire application, as was the case in the previous lecture. Now the canvas is just another data attribute of a new class, which is an extension of the class point, where we extend the class point with a data attribute, a canvas, and a method to draw a point on canvas. Why make such a fuss about this? Well, that will settle the conventions for what comes later. So all other classes, the lines and then also the parabola, they don't need to be concerned how a point is represented on canvas. Here are 10 random points, so there will be 3 canvas widgets that pop up. So there are 6 classes. 3 classes are concerned with the essentials of the data. The other 3 classes are concerned with the visualization. So here we have the representations for points. Okay, what is now a line? Um, A line, you could say, is y equals ax plus b, where a is the slope and b is the intercept. But then you have a problem with vertical lines. So you can represent um, a vertical line also with this equation a plus b y plus c. But then you have the problem that if you are dividing the coefficients a, b, c by the same non-zero number, you still have the same line. So you have to deal with the notion of equivalence classes. Not too good. So it's an algebraic expression that is not suited for geometry. For geometry for drawing. So we will need to decide on one parameter when we um, are taking points on the line. So how can we solve this? A better geometric representation of a line consists of a basis point and a direction. The direction is defined by an angle. So a line, if you like, is an extension of a point where you extend it with an extra data attribute, an angle. And a point then belongs to the line if you can actually go from the basis point in the direction of the angle to the point. So that's the membership problem, but we will not use this. We will actually use this representation as a very convenient representation to take points on a line. So a line that can be drawn in any direction. So if the theta is pi over 2 is 90 degrees, then we have a vertical line. So we can, with this representation, we can very conveniently draw a line. All right, we inherit. So this is so every class will be stored in a module. The module contains the class definition and some examples on how to use the class. So if we have the class point defined in the class underscore point and the class line defined in the module class underscore line, then we can make a line passing through the point 3, 4 and with angle 1.23. So because of this inheritance, we have that the line is also an instance of the point. So we can interpret this by saying that the line is an extension of the point. In some sense, you're not limited to staying at your basis point, but you can move in one particular direction, the direction that was defined when the line was instantiated. This is a lecture on class hierarchies. One could design this differently. One could have inside a class line, one could have a data attribute that is point. Um, so this is different from inheritance. The class parabola will inherit from the line, but will have the focus as a data attribute. Okay, so then we see the line as a function by overriding the built-in call method. So call is a built-in method. If you override it, if you give it a definition for your class, then you can use any object as a function. So this will be extremely useful. So this is the definition of a line. Has nothing yet to do with drawing the line, but we're already thinking geometrically. You see that when you define, when you are building your design, we are building bottom up, but we are building towards the goal of drawing things. So that's why you are thinking geometrically. So for algebraic purposes, this might not be so good. So just to emphasize this, it depends what you want to do with your objects. What kind of methods, what kind of data attributes will you store? So for a line, we have three numbers, the coordinates of the basis point and the angle. And then you see that the mathematical formula here for any point on the line is actually implemented by the call method. And we return a point. So we compute the coordinates, the x plus t times cosine of theta, and the y plus t times the sine of theta. And with these two coordinates, we make a point. Here is the result of show lines. So we have 11 lines. Why 11 and not 10 random lines? Well, one of them is actually not really random. It's a vertical line. So visualizing the vertical line is kind of difficult because you have to decide on the range of your parameter t. So how many points should you take? Well, you take as many till you leave um, the width of your canvas. For a vertical line, this doesn't really work. So the vertical line is actually a special case. I will indicate how this works in the code. To show a line, we are extending the line by inheritance. So we are inheriting from the class showPoint. The class showPoint has a method draw to draw a point on canvas. The class showLine will also export a method draw to draw a line on canvas. So this is another illustration with multiple inheritance in the context of visualization. What the draw method will essentially do, it will compute the ranges where to evaluate your line. So we have multiple inheritance. Whenever we inherit, we have to call the constructor of the base classes, of the classes we inherit from. So we inherit from a line, so we pass the coordinates x and y of the base point and the angle. When we inherit from the show point, we pass the canvas C, and also we are passing the coordinates of the point. So in some sense there is some redundancy here. So we are going to store the coordinates of the point twice. Once as the base point of the line, and once when we are going to show in the show point. The other data attribute that is passed, so the other argument that is passed in the constructor of a show line is the dimension of the canvas. And that is necessary, so that's an essential data attribute to draw the line on canvas. So you can also see object-oriented programming as a way to make sure that all the arguments of the functions, which are now methods, that all the arguments of the methods are actually correctly passed through. Okay, so what is the benefit from this design? When we draw the line, we don't really need to think about how to represent the base point. So we inherit from show point actually the draw method. The draw method for a point. Um, Points on the line will be represented differently. So in some sense, uh, there is also an equivalence. So there is not a unique way. So any point on the line can serve as a base point, but the base point is kind of to indicate what is kind of the point of departure when you draw the line. Lines go on forever, but actually it doesn't matter. It doesn't really matter that you draw them outside the range of the canvas. So um, we store the canvas and the dimension of the canvas. So that is important. There might be an attribute to get it from the canvas, from any canvas object. You may most likely get the height and the width, but here we actually store this separately. Our canvas widgets are square. So it does not, so we have to compute the value of t where we get to the dimension d when we add to it. So if we go to the one of these sides, that is then solved by a very simple computation here. Now notice that if the cosine theta is 0, that happens when you have a multiple of pi over 2, uh, then actually you have a vertical line. And this formula should not be applied in case of a vertical line. That's the special case. I will show how to resolve this in the code. So now get to the second part. The goal, essentially, we have two more classes to describe. We want to visualize any parabola on canvas. So if you are taking the standard expression that defines a parabola as a quadratic formula with three coefficients a, b, and c, then you're very limited. So you can actually only define concave up parabolas like this or concave down parabolas like that. Not very good, because actually you have also parabolas that actually go that way. So let me mark this down. So if you are drawing quadratic formulas, then you're limited to this, but you can't really do parabolas like this. So you could say this is a square root, but it is not. So it is actually a genuinely good parabola, and here I'm drawing this rather bad. But any case, so what is a parabola geometrically? It's the set of points at the same distance from the focus, a point, and the directrix, which is a line. So thus, we define a parabola by given a focus and given a line. So the focus is two numbers. The directrix is three numbers, a line, the base point and the direction of the line. So 5 numbers suffice to define a parabola uniquely. So we will draw, in this application, random parabolas. Here is such a random parabola. So notice here, if you were to verify this, this is the focus. If you go from the focus straight to the line, so I'm not really going that straight, but you can see that this line segment here and that line segment here, they have the same distance. You can also go to any other point, and then going from the parabola to the line is also going a straight line perpendicular to the directrix. Also here you can see, you can kind of verify that my crooked lines don't really show this too well, but you can also see that the black parabola here will collect all points that are at the same difference at the same distance from the focus and this directrix. Okay, so that is actually the main goal for the program, that we have a very good way to draw parabolas on canvas. Okay, I mentioned the different designs when we when we were defining the line, we inherited from a point. We could also have that the point is a data attribute. Here the focus will be a data attribute. So the fx, fy are the coordinates of the point, and the point is a data attribute called focus. We inherit from the line. The line is defined by three numbers, the base point p, x, p, y. So these are the two coordinates and the angle. So there is a difference in the sense that a parabola is an instance of a line by inheritance. You could also say that a parabola extends the line. And the parabola has an instance of a point as a data attribute. So there is the is instance and has a instance as data attribute. Okay, then we will also, for drawing purposes, we will be drawing by evaluation. So our parabolas will also be callable. When we draw a parabola, we take points on the parabola. And we have a parametric representation of the parabola. We can run along all the points of the directrix. And for every one of those points, we are on the line, and then we compute actually the intersection of two circles. So it's the circle, we want actually to find the point on the parabola, and the point on the parabola is at the same distance from the point on the directrix with coordinates cx, cy, and at the same point from fx and fy. This will lead to a linear system in alpha and beta. There are more. There is one constraint here, so that's the quadratic equation. But then we have the line that is spanned by the point alpha beta, and the point is actually orthogonal. So that actually gives the other condition. So that will give the linear system in alpha and beta. All right, here is how this is solved. So if you are looking at these equations, they are quadratic equations, but you can eliminate. So there are linear equations in alpha and beta. So here this is an example of symbolic computing. So algebra, computer algebra and programming, they're actually related. So if you want to see an example, there are many examples that will be coming, but the kind of cruel thing is before you can see many examples, you have to follow the algebra. So I have the equation here that is fully expanded. So if I expand both sides here, I can eliminate the alpha square and the beta square here. So they are the same. So this equation equals that equation. So the alpha square, beta square, you subtract this. And this gives then a linear equation in alpha and beta. The other equation is expressing that when you go from a point on the parabola to the directrix, you go in a perpendicular way. So this gives then the other. So this is then illustrated by a dot product. So the prerequisite for this course is calculus. So we do some symbolic algebra here. So that is the main difficulty that will be, so algorithms are not central anymore as they are in procedure-oriented languages, but that doesn't mean that there are no algorithms in the methods. So the method to actually draw the points, or actually the method that makes parabolas callable will actually store this algorithm to compute the coordinates of the point, the coordinates alpha and beta. All right, so to um, complete this system, so I mentioned the dot product here. So the dot product expresses the orthogonality. So that's the second equation. So it's an equation in the unknowns alpha and beta. When we work with matrices, we separate the given numbers. So what is again given? So we have the coordinates of the focus. We have the coordinates of the point on the line. Um, we also have the x and the y. So the x and the y are actually here also known numbers. So we can find explicit formulas for alpha and beta with Cramer's rule. Cramer's rule allows to solve the linear system via determinants. And doing this via determinants is very good here because we can see when this matrix here has a zero determinant. So that will be a special case that we will handle in the code. So here you see the start of the code. The discriminant here is the determinant of this. We have the coordinates of the base point here. So here you see the discriminants. So we have the focus, the coordinates of the base points, and then also the point um, that is stored. Um, so we inherit from the line. So by inheriting from the line, we have the base point of the line. So that's actually what this x and y is. Um, okay, so the line is when you evaluate the point. So calling it here line with a little l is a little bit not good. It's a point on the line. So we have a point on the line, the x and the y coordinates. So this is the cx is line dot xpt, cy is line dot ypt. So this is the start of making the parabola callable. So the parabola is parametrized by walking on the directrix. Um, again, we will draw the directrix. Again, we will have a range for the directrix. All right, so then the last class definition. So again, it's in some sense we are following the same pattern as before. So I started out by showing a point, which is rather a trivial class. Then showing a line is not so trivial anymore, but still everything is nice linear. We solved one equation there. In order to make a parabola callable, we had to solve a linear system. So it's that algorithmic complexity that is hidden. And you can now kind of understand why in very elementary algebra classes people stick with the y equals a times x squared plus bx plus c. Because if you have to do this by hand, and many courses are still set up to make you do computations by hand, you won't get through it anyway, through these complicated formulas. But as programmers, we can reason with abstract coordinates, we can do algebra, and we can then generate as many examples as we like. All right, there are only two exercises here in the second part, the lecture following. There will be many more. So there are the mouse events. So you can actually walk through. So the user can, and also we will give random parabolas, but you may want to design your own parabola. See what happens if you start moving the directrix. So what you do here, with this first exercise, you might do this first for the line. Or here it's the focus of the parabola. So this is allowing that you grab the coordinates of the line of the focus and you move it. The action, the method that is then associated to you moving the focus is actually entirely redefining the parabola and redrawing the parabola on canvas. So you make a new parabola, you wipe the canvas clean, and then you draw the parabola again. Um, we've seen animations, so you could show how the parabola is actually drawn in an animation by a point that moves on that directrix. So this is kind of a sweeping. This could be good. So now we will see the parabolas all at once on screen, but this could be another good geometric application to actually understand what parabolas really are geometrically. Okay, so this is the design. So I have 22 slides, half hour in. So I have prepared a Jupyter notebook. So there are 6 classes, 6 scripts that are posted. The first, oops, I should not go all the way here. So what I should execute is the definition of the class of a point. So here you see a point, 3 methods, but you can see how the representation. So if no arguments are given in the constructor, then we have the origin. If we want to define a point, say the point 3, 4, then we pass the coordinates. And the representation, so when I type in P in a code cell, then what is executed is the representation which gives the string representation. A point is essentially just a tuple. We don't need a class for this, but this is just to make this lecture self-contained. So what is a class? A class is defines our types. So it's actually encapsulating the tuple. There is the class point. So here is this class point. It's defined in a module with a main program. So we can run this class point as a program, then the main program is being executed. And that simply illustrates how to use this class. The class is here simply serving as storing the coordinates of a point, encapsulating the tuple. Okay, visualization then. So in this project, in this lecture, so in some sense, yes, this is a project. We are graphing things, but unlike the previous lectures, where the emphasis and the focus was on the graphical user interface, now actually Tkinter plays a subordinate role, and we will only use one widget, and that is the canvas. So to define the drawing of a point, we make a new class showPoint. So in a way, what the classes are doing, they are defining algorithms to graph geometric objects. But in order to do that, you need to have data as well. So you need to have a canvas. So the canvas is passed as a data attribute. Now, actually, a canvas is what is passed is actually the reference to the canvas. And what the show point does by inheritance, so we call the constructor. So the constructor will store the coordinates. So we make a point essentially, and we extend the point with the canvas. And this show point class defines the convention on how we will draw a point, how we represent a point on canvas. We will reuse this convention when it comes to drawing the base point. Okay. So we have one canvas, so we make a window, we make 10 random points, we draw them, and then here you see what comes up, the 10 random points. So the main event loop is now on, so I have no methods associated to the GUI. Um, there are no mouse bindings, so one could eventually also here allow that the user starts to grab the points whenever uh, it is the mouse is in one of those circles, then you could allow to drag the points. Okay, up to the class line. So far so good. Um, in a way, we have defined two elementary classes and seen again the tkinter, which is part of the Python framework. Framework is a collection of classes that makes Python really useful. All right, we need the cosine and the sine when we want to evaluate a line. So here is the line. So the line inherits from the point. So we have three numbers, the coordinates of the point and the angle. So the angle is an extra data attribute. We define the string representation. This is just to test out this class. Um, and then we can run. So when passing no arguments, we have 0 angle, 0 point. We have simply the horizontal line. Let's make a vertical line. So you can see it's the horizontal line. Any point will have that you make on that line will actually have a second coordinate that is 0. We will then make a vertical line. So if you go 4 steps up, then your y coordinate will increase by 4. And what you will have, of course, here is that your first coordinate remains constant. So perhaps I should also show the class line. So here you have the scripts. So this is a sequence of scripts. So the class line imports from the class point. So we import, so the class point can serve both as a program, but also as a module that exports the class definition of point. So here is then the test program, what I executed in the Jupyter notebook. Okay, showing a line on canvas now. Now it gets a little bit more complicated because we have to define the range of the value. So and we also have a case of multiple inheritance. So these imports are actually not necessary and I should remove them. They don't harm, but they're not necessary here. So I will do multiple inheritance. So to show a line, I inherit from the line and I inherit from the show point. In this way, the showing of the basis point, of the starting point when you walk on the line, is then actually already defined. So you see here when we draw, we just draw, we call the draw method on of show point. Um, Passing self, and self actually has the canvas in there as well. So here you see C is the canvas. So the canvas is passed to um, show point. Okay, um, inheritance. We inherit from the line, extending with the data attribute d, which is the dimension of canvas. Okay, so then we have this formula that uses the cosine of the angle. We divide by this cosine, and the cosine better not be zero. Now, being zero in the double floating point terminology means that there is actually an entire range of numbers. So any number that is smaller than the machine precision will also be regarded as zero. So here, if the machine precision is defined as the smallest number you can add to 1 and still make a difference. So if you don't make a difference anymore, so then you have a vertical line. And then actually we create a line. So then actually this special case can be handled extremely quickly. So we have a vertical line where the x-coordinate doesn't change. So we create a line. So creating a line is from the start point, the bottom of the canvas, to the top of the canvas. So you can see how this works. So what I do is I compute the end points where I have the beginning and the end ranges, and I create a line. You may have observed that when some of the lines are close to being vertical, they actually do not intersect the left and the right bound of the canvas. So in some sense, the lines that we're going to make are way too long, but it doesn't matter. So for the visualization, it is not a problem to go out of bounds with our points. Okay, so we call this formula here. So the difference between the dimension and the endpoint to the right and then to the left. So this is the other equation that is solved in here. Okay, so twice evaluating the lines for the endpoints on the line. All right, let's draw some random lines. So I make a window. 400 pixels wide. Here are all my lines. So this is where we make the data attributes. Then the drawing is defined, and then in the event loop, the rendering is done. So here you see 10, or actually you see 11 lines. The vertical line is here a special line. All right, this is all preparation to get to the showing of the parabola. I have less than 10 minutes left, but I hope you kind of um, get the appreciate the approach of working from the bottom up. If you can't draw the directrix properly, then you can't really draw the parabola. So the show line is still a relatively small class. So that's also what I should have pointed out. So just two methods in there. Pilot might actually tell me too few methods in a class. Pilot might be concerned that I'm making a class, but actually there's no need to. In a computer-aided geometric design, you may indeed need much more to represent a parabola, to work with parabolas in general. Okay, so the parabola inherits directly from the line and has the point, the focus as a data attribute. So here is the constructor, there is the string representation, and then there is the entire complexity of this evaluation of the line. And this is where the algorithmic complexity comes in. So looking at the code makes this almost incomprehensible. I should actually go back to the slides. This was introduced by the slides. So here you see the linear system that we are solving via Kramer's rule. So we solve it symbolically. So in some sense, if you are a programmer and you start with writing non-trivial programs, you can't really do without algebra. So you have to think about letters that take in the place of numbers when you run the program. Okay, so here is the code. The Kramer's rule wants me to construct the discriminant. And here you see when that discriminant is non-zero, I was here forcing the correct divisions. So the floating conversion was not strictly necessary. So this was dating back from um, Python 2, where you would run the integer division if the arguments were all integers. But I'm distracting here. So what I'm doing when I'm solving it, I'm setting up the right hand side. So this is in the general case. In the general case where things are running fine, when is the discriminant being zero? Well, the discriminant is being zero if that determinant here is zero. When does this happen? Well, the x and the y are the coordinates of the base point. If the coordinates of the base point of the line are such that they make the same difference with the focus, and that will happen only for one particular choice, then in some sense, this discriminant checking is kind of rather exceptional. However, we are running this throughout, so there might still be, if we run through our directrix, might still be the case that this happens. How do we solve this then? Well, I just take another point. So this is solved then by taking another point. So here I probably should have taken a random point, but I take a transcendental number for my line, for my base point of the line. And then I recompute the discriminant and do the same Kramer's rule again. So strictly speaking, for this course, this algebra is not necessary, but this is good to indicate where the hiding of the complexity lies. So if you think about visualization, you might not think about solving linear systems, but it is essential. And that is handled by this class here, which doesn't care about visualization, which just makes your parabola into a function. So here we have it. We have the parabola, and which we evaluate. This is not that much of a test. So I mentioned the membership problem. So can you now actually, so a test would have been to give a polynomial, to give a quadratic, the y equals ax squared plus bx plus c, and check it for there. Check it for a very simple case that you can verify by hand. Here I was confident enough in my reasoning, also because it was validated by the plot. Okay, I'm coming to the essence of this, and here you see now the benefit of top-down. The end result is a class to draw a parabola, and now you see that the drawing of the parabola is drawing the focus. So I'm doing the inheritance. So I'm inheriting from the parabola, I'm inheriting from showing the line. So drawing the parabola is drawing the line, it's drawing the focus. So drawing the focus is now a separate method. Um, so in a way, I'm using the same conventions here, but you could use another color for the focus. So instead of sky blue, you could draw the focus in red, for example. The focus is a very special point. It's different from any other point, the base point. And I select a range. So here I wasn't so careful about, so I could have taken the same reasoning for the range of the directrix. So when you draw a line, you can actually, based on the dimensions of the canvas, for any particular line, you could actually have the range for the line stored this as a data attribute. I didn't do this, so this would be a more efficient design. I could have recomputed this here, the same formula, but what I'm doing here, I'm evaluating the parabola between minus 1000 and 1000. Um, more than 2000 points, 2001, or actually, no, exactly 2000 points for the computer, no problem. Okay, I'm running over time. Let me show the last demonstration. So here you see the random parabola. I ran through the code. Um, in the code, you see what I'm doing. I'm giving a random points, kind of in the middle of canvas, um, random focus, random directrix, random angle, and here you see a general parabola. Okay, I hope I made the point through one application how useful the inheritance is. Along the way, we had to solve an algebra problem, and that algorithmic complexity is encapsulated in the class parabola. The class show parabola is no longer concerned with that. So that is also the benefit how you can do the information hiding. You hide the algorithmic complexity, not only the data, but you hide the algorithmic complexity.